Hello! In this video, we will cover quadric surfaces and cylinders. In particular, what we will learn to do is we will learn to identify and create rudimentary sketches for both objects. Okay, so let's start with cylinders. A cylinder is an object that extends perpendicular to one of the coordinate planes. So to give you an idea of what we're discussing, let's just put a quick sketch. So this is a cylinder. And as you can see, the cylinder so it's an object that is extending perpendicular from, in this case, the XY plane. Okay, so it's extending perpendicular from that plane. How do you recognize or identify a cylinder? The way that you can tell when you have a cylinder is when two of the three variables x, y, and z are present in an equation. Examples. So for example, we could have x squared plus y squared equals 4. That's an example of a cylinder. Y equals sine of z. That's an example of a cylinder. X times z equals 1. That's an example of a cylinder. Okay, as long as you have two of the three variables, x, y, and z, present in an equation, then you end up with a cylinder. How do you sketch a cylinder? How do we create a rudimentary sketch? What we're going to do is we're going to draw the object defined by the two given variables and then extend it in the direction of the missing variable. Okay, so let's go through and try that with some examples. Let's say that we wanted to go through and graph the cylinder x squared plus y squared equals 4. The ways in which we can tell this is a cylinder. Oops, cylinder because we have x and y, but no z. Okay, and now let's go through and try and sketch it. The first thing that we want to do is we want to go through and graph the object that is defined with the two variables that we have. And the way that you do that is you're going to graph it on the plane of the two variables that are given, right? So we're going to graph x squared plus y squared equals 4, and we're going to graph it on the xy plane. Okay, so how do you do that? Well, so if what you can do, probably the easiest way to do this, first of all, is to recognize that this is a circle of radius 2. But what you can do is you can go through and you can just find intercepts for it. If you set y equal to 0, for example, then you'll get x equals plus or minus 2. So you could go 1, 2 units, place a point, 1, 2 units, place a point, right? So this is where y is 0, is what's going to get you the x-axis. And so you'll have points here and here. And then you could set x equal to 0, which would get you the y-axis. And then you could go through and do 1, 2, place a point, 1, 2, place a point. And then what you want to do is just connect those 4 points with a smooth curve and just do your best to try and make it look circle-ish, right? So the issue is that it's is that you're looking at the circle from an angle, so it's going to look strange. It's not going to look like a regular circle. So that's pretty good, except maybe this backside's a little wonky, but I'm writing with a writing tablet, so that's as good as it's going to get. All right, so go ahead and graph the object that's defined and graph it on the plane for the two variables that are given. And then once we've done that, we want to extend it in the direction of the missing variable. So the missing variable is z. So we want to extend this in the z direction. And there's a couple ways you could do this. What I typically do is go through and take the object that I've drawn here, and I just draw it again above the object, in the direction, of the missing variable. I go through and I just draw it again in that direction. So I take this point here and I just say, okay, well, I'm going to say this is my center here. And then I went 2 units in the x. So I go 2 units in the x, 2 units in the negative x, 2 units in the y, or negative y, positive y. And then I just, try and draw another smooth curve. And to see, this one was better than that one. And then at that point, once you've drawn it a second time, you can just use some connecting lines to kind of show the fact that it's extending. And I'll usually draw them through the points that I plotted, right? So I plotted points here and here, here and here, here and here, and backside. So one little trick to try and get your picture to look right is to have the ends of the lines that are, that are on opposite sides like this, to have them end in the same place. Notice how I did that. essentially in line with the y-axis, right? If you took the y-axis and just set it up here, it would fall right on them, right on the tops of the two lines and on the bottom of the two lines. And then on the front and back, those are lines that are on the x-axis, and so you want the tops to align with the x-axis. That will give you the correct kind of dimensionality to the picture, and so it just kind of enhances your graph. Okay, so that's the sketch. Oh, and second step here is to extend in the z direction, which we did. All right, so it's 2 steps for these sketches: graph and extend. Okay, let's go through and try another example. Again, we can recognize this is a cylinder due to y and z being present, but no x. Let's draw a coordinate axis so we can sketch this on. And again, to go through and sketch, we first want to go through and graph y equals sine z on the yz plane. And then when we're done, we will extend in the x direction. Okay, so how do we go through and graph y equals sine z? Well, you'll notice that the way that it's structured here is it's structured so that y is the dependent variable and z is the independent variable. In other words, we plug stuff in for z and then we find the result for y. So z is what we plug in for, that's the independent variable, and then the dependent variable is the result of that. So because of that, what we should do is what we can do is go through and pick z values and then find the corresponding y values and then just plot points. Okay, so the YZ plane is the plane that you're looking straight at. All right, it's made up of the Z-axis and the Y-axis, so just ignore the X, pretend it's not there, and you just have these two. And then what we want to do is pick Z values and then 5 corresponding Y values. All right, so if Z is 0, sine of 0 is 0, so we'll have a point right there. And then the next value that you typically would plug into a sine function might be pi over 2. So just pick a spot to be pi over 2. And then if you plug pi over 2 into the sine function, you end up getting 1. So we want to go and we'll say this is 1 unit. And then we could go through and say, here's pi. If you plug pi into the sine function, then the output is 0. If you plug in pi over 2, or 3 pi over 2, you get -1, which we'll say is right here. And then if you plug in 2 pi, you'll get the point there. And then it keeps going, of course, right? So it keeps going. And it keeps going in the negative direction over here as well. So we can just pick a spot there. And then let's just do your best, try and draw the curve in here. So it's going to look something like, let me try that again. The writing tablet is difficult to use. Like that. Like that. Like that, and then we'll just stop there and say that's good enough. Okay, so that's the graph of y equals sine z. And then to go through and extend that in the x direction, again, the way that I typically do this is I just pick I go move in the x direction, right? So all of this was on the yz plane. It's sitting here where x is 0. So I'm going to move in the x direction, pick a spot, And then I'm going to go through and just do the exact same thing. And you could even put in a dashed line here to represent, say, all right, you know what, this is going to be the z-axis here. And I could go up and I could say, all right, so I've got this point corresponds to this point, and then I could go up pi over 2, and I would end up with the point here. And then at pi, I get this point, and just do your best to try and line it up, right? So, and then at 3 pi over 2, we ended up with this point, and here we got, this is 2 pi, and then here we got another point over here. And then there was, we did put a negative point. So go through and try and draw the sketch and just do the best you can. And we've got our curve drawn a second time. And then to go through and kind of show the dimensionality, you just want to put in some lines to kind of connect the dots here. So we've got a line there. There's a line there. We have a line here on the back side. All right, there we go. And one more here, or a couple more. Let's put a line here. Oh, that one's off by a little bit. And finally, a line up top and a line on the bottom. Okay. So it can look a little odd in places where the lines end up on top of each other because of the angle that you're looking at. And that's kind of right in here. You can see where this line ends up on top of that line, ends up on top of that line. So it looks a little screwy, but that is the accurate, that's the picture. It's just, that's where the lines ended up falling, on a, if you had a wave function like this, that you were looking at from an angle like this, this part and this part and this part do end up all kind of on top of each other. And so that does happen. And you can see the same thing is happening in the, the variation of the structure down here at the bottom. Okay, so that's our picture. Let's try another one. Let's say we wanted to go through and graph x, z equals 1. And so we could say, yep, there's no y, thus it's a cylinder. Go through and graph a chorded axis. All right. So first we want to go through and graph xz equals 1 on the xz plane. And then when we're done, we will extend in the y direction. The xz plane is probably the plane that people who are learning for the first time find the most difficult to work with. What you want to do is just, again, when you're trying to graph on a plane, pretend this third line is not there. You only have these two lines, right? This is the xz plane, it's this flat piece of paper here, this flat object here that extends in every direction. And so you just want to graph the object on that flat plane. And to do that, just pretend the y-axis is not there. All right, so how would we do that? Well, similar to the other two cases, you can go through and you can plot points. So you could go through and you could pick an x value. So you could say, all right, well, let's say x was 1. If x is 1 here, what would z have to be for this to be true? And z would also have to be 1. And so you end up getting the point 1, 1. All right, if you picked x is 2, if x is 2, then z would have to be 1/2 to offset that. And so if this is 1 unit, then half that would be maybe here. And you could go through and do 3. If x is 3, z is 1/3, which is going to be even shorter. And then you could do the same thing on the z-axis. If this is 2 units, if z is 2, then x would have to be 1/2. And if this is 1 unit, then 1/2 would be right about there. Do be careful, right? So the x direction is at an angle here, so I need to do more like that. All right, and then we could go up to 3, and it's going to be even shorter yet. And so we get our points here, which if you go through and try and connect them, look something like, oh, let's try that last little bit again. Something like that. And you can also go through and do negative values. So lots of times when you're sketching pictures of objects, you might intentionally just sketch the positive part. So as long as it's intentional, that's fine. But you should be aware that there also is a negative piece. And so to go through and graph the negative part, we can put dashed lines in for the negative axis and then just do the same thing, right? So if we chose x is -1, then z would have to be -1. And we end up getting that point there. If x is -2, then z would be -1/2. So you want something that's about half that distance. And -3. And then you could do the same thing for z. If z is -2, then we want -1/2, which we'll say is right about there. And if z is -3, you get a point that's a little closer. And then you can just go through and do the same thing. We want to just connect these points with a smooth curve. Let me try that one more time. So one thing about going through and drawing the object is your object will look best if you have essentially the same length in terms of how far you extend the line. So you'll notice that this line ended right at -3. So we want this line to end about the same distance along. And so you'll notice the first time I drew it, I made it maybe a little too long. And so if you go through and have the lengths be the same in terms of how far you draw, above and below and in front and behind, that will give you the best, cleanest picture perspective-wise. Whereas if you draw this line extending a lot further, then it skews the picture and looks less recognizable. Okay, and so that's the graph of xz equals 1 on the xz plane. In order to go through and extend in the y direction, what we want to do is we want to just take this object and just draw it again by moving over in the y direction a certain distance. So you can go say, hey, I'm going to go right here, and I just want to draw this object again. And so similar to what we did earlier, what you can do is you can just kind of put in a fake z-axis over here and a fake x-axis and a fake -x and -z. And then what we want to do is just sketch this, and you don't have to put as much time and effort into as you did applying the points originally, but you could just say, all right, well, 1 is going to be right about there, and then this point will be closer and closer, and so on. You can just eyeball it and connect your points with a curve. You can see it looks pretty similar. And then do the same thing over on this side. So we could go 1 and 1. We get a point here, here, and here. And then finally, you can just go through and use some lines to just kind of show that this extended across. Just pick a couple points that you've got on there. Oh, just a second. Let's try that again. And then the same thing below. And your picture will look a little cleaner if the ends of these lines extend about the same direction distance. So this one maybe is a little short. It just will make your picture look cleaner in terms of the perspective on it. Okay. So that concludes the section on graphing cylinders. Next, we're going to go through and graph quadric surfaces. So first of all, what is a quadric surface? It is an object produced by a second degree equation. So you could think of the quadratic formula, right? The quadratic formula is for solving a second degree equation. A quadric surface is the object produced by graphing a second degree equation. So we're going to have a variety of different types of quadric surfaces. How do you recognize what type you have? Typically, you're going to have to memorize it. How do you sketch? What we're going to do is we're going to go through and produce cross sections by setting a single variable to a number. An example that hopefully will be the most familiar would be if we set z equal to 0. So if we set z equal to 0, this produces the cross section of the object on the xy plane. Okay, so let's go through and do some examples. So let's say we have x squared over 4 plus y squared over 1 plus z squared over 9 equals 1. Okay, so in terms of recognition, the fact that we have x squared and y squared and z squared, and they're all positive, this is an object that is called an ellipsoid. And the format of an ellipsoid looks like this: x squared over a squared plus y squared over b squared equals, plus z squared over c squared equals 1. Okay, let's go through and draw ourselves a coordinate axis, and we'll draw it nice and big. These objects can be a little bit difficult to work with. Okay, so once you have gone through and you've got your equation and we recognize, hey, that's an ellipsoid, the next thing to do is to go through and generate the cross sections. So what we're going to do is we're going to start off with z equals 0. And so this is the cross section that represents the xy plane. What it's going to produce is it's going to produce the part of the object that lies on the xy plane. So you're just going to take z equals 0 and plug it in up here, right? If we do that, it's going to get rid of that term there, and we'll have x squared over 4 plus y squared equals 1. Okay, so this is an ellipse, and you can go through and graph the ellipse by just finding intercepts for it. You can set x to 0 and solve for y, and set y to 0 and solve for x. So the intercepts you end up getting is you're going to get +2 and -2. Oh, and one other thing too. Once you've generated the cross section, so it's on the xy plane, you want to take this object and just graph it on the xy plane. All right, so we want to go ahead and draw the ellipse on the plane that's represented by our choice for the equation here. Since we set z equal to 0, that got us the xy plane, so we want to draw this object on the xy plane. And so you're going to get x equals plus or minus 2 if you set y to 0. If you set x to 0, you're going to get y equals plus or minus 1. And then you just go through and draw a curve for that. Connect those points as best you can. Okay, and then to continue generating cross sections, typically we're going to go through and use the xy plane, the yz plane, and the xz plane for our cross sections for our objects. And then if that's not enough to tell what the object looks like, then you can generate more cross sections by picking values for x, y, or z that are not 0, and that will generate cross sections that are parallel to the coordinate planes. Okay, so next we could go through and we could set x equal to 0. This is going to give us the part of the object that's on the yz plane. Okay, if we do that, we end up with y squared over 1 plus z squared over 9 equals 1. And so again, we want to go to the yz plane. That's the one you're looking straight on here. And go ahead and you can use intercepts for this too. If y equals 0, then z will be plus or minus 3. So you could go 1, 2, 3, place a point, and 1, 2, 3, place a point. And then we could go through and set z equal to 0, and you get y equals plus or minus 1, and you can see those points are already there. And then just draw a smooth curve. Do your best to kind of make it look like an ellipse. Like that. And then we could go through and set y equal to 0, and that will generate the part of the object that's on the xz plane. If we do that, we end up with x squared over 4 plus z squared over 9 equals 1. And then you can use intercepts to graph this. So the xz plane, that's this plane here. And so we'll get intercept at x equals plus or minus 2, and it's already there. We have z equals plus or minus 3, already there, and then just connect the points with a curve. So we're going to try and bow it out like an ellipse, right? So it's going to look something like that, 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 and that. Okay, and so that's your object. It's maybe a little bit difficult to see, but it looks kind of like a football, right? It's like an oblong sphere. Now, the one thing I did want to show you before we move on to the next example is that, again, you can generate cross sections other than the sections that are on the x, y, y, z, or xz plane. So you could go through and you could say, how about z equals 1? Right, so what plane is represented by z equals 1? right? It's the plane that is parallel to the xy plane, but shifted up 1. So it's the plane that's located right here that is parallel to the xy plane. So if you put a piece of paper right there at z equals 1, you would end up getting the plane z equals 1. All right, so if you go through and take z equals 1 and plug it in, you're going to end up with the cross section that's sitting right there. All right, so let's see what happens when we do that. We're going to get x squared over 4 plus y squared over 1 plus 1/9 equals 1. Then you could move the 1/9 over, and we'd get x squared over 4 plus y squared over 1 equals 8/9. Okay, and then this is an ellipse. The way that you can recognize an ellipse in terms of the object, the equation, and that is that if you have x squared and y squared and they're both positive and the denominators are not the same, right? So since we have 4 and 1, we're going to have an ellipse here. And the form for the ellipse is you divide over the 8/9. So if we divide by 8/9, this will end up turning into x squared over 32/9 plus y squared over 8/9 equals 1. Okay, so if we, again, we want to take our object now, our cross section, and we want to graph it at z equals 1. To do that, you're going to start at z equals 1. That's where our plane is located. And then you could use this equation to find intercepts, right? So if you set x equal to 0, what you're going to get is that y is plus or minus the square root of 8/9. All right, so on our picture here, if you go 8/9 in this direction, you're going to hit this curve here. If you go 8/9 in this direction, you're going to hit the opposite side. So this distance here should be the square root of 8/9. All right, so that should be that distance there. And then if you go through and you set y equal to 0, you're going to get plus or minus the square root of 32/9. And so if we start here and we go in the x direction and you go the square root of 32/9, you should hit this curve, which represents the curve that is opposite the x-axis, or that's aligned with the x-axis. You should hit that curve. Yeah, it looks like somewhere right about there. And if you go in the negative direction, square root of 32/9, you should hit right about there. And so we could go through and draw another smooth curve there. You can see that makes the object a little bit easier to see. You could go through and do the same thing here at z equals 2. Whatever equation you end up getting, if you go in the y direction, you're going to hit the curve here, negative y here, x here, negative x here, and you'll get another cross section that looks like that. And you can go through and you can generate cross sections up and down the object. And again, just to be clear here, z equals 1 is just an arbitrary choice. You could have gone to x equals 1 and you would get a cross section that looked like that. Now that would be quite adventurous to try and graph that on your picture and have it not look like a mess. But you could try it. And anyway, the point is that you could go through and generate anything you'd like by plugging in z, x, or y equal to a constant. Now, a question that frequently does come up, well, what would happen if we set z equal to 4, right? So you see how we go 1, 2, 3, and then the object stops at 3, and then you get to 4. If you set z equal to 4, you should get an equation that has no solution. So if there's no part of the object, where you're plugging in, then it should not work. All right, that should be the outcome, is that you get something that doesn't make sense. Okay, so there's our first example. Next, let's look at z equals x squared plus y squared. All right, so first of all, what is this? It is a paraboloid. How do you recognize a paraboloid? A paraboloid occurs when you have one of the three variables is to the first power and the other two are squared. So here is the general format for that. In this case, this would be where z is by itself. However, you could also have x by itself or y by itself, and you'll still get paraboloids. We'll talk about what type of paraboloid you'll get at the end once we're done graphing it. All right, so let's go through and draw our coordinate axis. Okay, and so we want to go through and generate cross sections. So to generate cross section, we could set z equal to 0. That's going to be the cross section that aligns with the xy plane. If you do that, you're going to get 0 equals x squared plus y squared. So the solution to 0 equals x squared plus y squared is going to be x equals y equals 0. It's just the point here at the origin. Okay, let's go through what if we set x equal to 0, then we would get z equals y squared. Okay, so that is a parabola, and we want to graph that. So x equals 0 is the yz plane. We want to graph that on the yz plane. So if you're graphing on the yz plane, pretend the x is not there. We just have the z and the y. All right, to go through and graph that, y is the independent variable and z is the dependent. So you want to plug in y values and find corresponding z values. So if you plugged in y equals 0, z would be 0. If you plug in y equals 1, z would be 1. We plug in y equals -1, z would be 1. Y equals 2, you get z equals 4. -2, 4. And we could go through and just draw a smooth curve through those 5 points. Okay, and so that is our curve z equals y squared drawn. That's our cross section that's drawn on the yz plane. Let's go ahead and do y equals 0. If we do y equals 0, we get z equals x squared. So same type of object, except on the xz plane instead, and you want to do the same thing, except now x is the independent. So you want to plug in x values. So if you plug in x equals 0, you get z equals 0. If we plug in x equals 1, you're going to get z equals 1, so it's going to be right about there. If you plug in x equals 2, you're going to get z equals 4, which we said this distance was 4, so let's just do, it's going to be right about there. Okay, and then we could do the negative direction. So if you go -1, then you go up 1. And the other way to line it up is that this should be, if you started here at 1, it would go 1 unit in the x direction. So you don't have to go 1 unit in x and then 1 unit in z. You could go 1 in z and then 1 in x, if that makes it a little easier. That actually maybe does make it easier. So in this case, the next one, instead of going 2 and then 4, I think it's easier to go 4 and then 2. Okay, and then so that gives us our 5 points. Draw a curve that goes through those points. And so we end up getting this is what we've got for our picture so far. And so frequently, this is something that we'll do without going through and doing additional cross sections. See this point here, 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 and here? Those are all points that are all at z equals 1, right? Recall we went 1 in the y, 1 in the z, 1 in the x, 1 in the z. They're all at z equals 1. So they're all at the same height on the same plane. And so you could just connect the dots, connect the curve here. And the same thing here. All of these 4 points are at z equals 4. And so we could just draw a curve that goes through them. Now, if you wanted to formally generate those, you would go through and you would say, all right, well, what do I get if I plug in z equals 1? If I plug in z equals 1, I get 1 equals x squared plus y squared. That's the circle of radius 1. And if you look, yes, this is 1 unit. This is 1 unit, right? And so it's 1 unit in every direction. And similarly, up here, we would have z equals 4. And you could formally do that. Now, typically, I will not do that. I will just go ahead and connect the dots without formally creating another cross section. And again, so you get the circle of radius 2. And if you check here, this is 1, 2 units, 1, 2 units. And so it does have a radius of 2. And so this is our picture. Okay, so here's our paraboloid. It looks like a bowl, right? Or sometimes people say it's the head of a bullet. So the one thing that I did want to comment on now that we have our picture, so the ball opens around, if you want to think about this, like it's opening around the z-axis, it opens around the variable that's to the first power. Okay, so since we have z to the first power here, that's why the opening is about the z-axis. If we had x by itself, then the opening would be about the x-axis, and the bowl would open toward us. And if we had y by itself, then the bowl would open to the right. Okay, so those are the different types of paraboloids. The specific equation here is for the bowl that opens upward or downward. You could have downward if c were negative here. Okay, so that's our paraboloid. Next. Let's say we have x squared over 1 plus y squared over 4 minus z squared over 9 equals 1. This object is a hyperboloid of 1 sheet. A hyperboloid of 1 sheet has the form x squared over a squared plus y squared over b squared minus z squared over c squared equals 1. Okay. Or, well, I should say, this is one type of hyperboloid. If the negative is on the y or on the x, then you get a different type of hyperboloid of 1 sheet. And I will summarize that at the end. So let's go ahead and create our coordinate axis. And let's generate some cross sections. So we could go through and set z equal to 0. If we do that, we end up with x squared plus y squared over 4 equals 1. All right, so that is going to be an ellipse where we have intercepts of 1 and negative 1 for x, and 1, 2, 1, 2 for y. And just draw your curve as best you can. Okay, and then next we could go through and we could say, how about x equals 0? If x equals 0, we get y squared over 4 minus z squared over 9 equals 1. Okay, so this is a hyperbola. I'm going to go through and use the box method for graphing the hyperbola. If you're not familiar with that method, then you may want to go through and try and watch a video to see that. I'm not going to cover it here. Okay, what the box method requires that you do is you go through and you use the square root of the denominators here to identify what act like intercepts, okay, what act like important points. So we're going to get, for y, we get -2 and 2, and you'll notice we already have those. And then for z, we get 3 and -3. So we have 1, 2, 3. Okay. And then using the dashes here at the top and bottom, and on the left and right, you form the box. And then the asymptotes go through the corners of the box. And again, if it's been a bit since you've graphed a hyperbola, then that would be a video worth looking up. And then once you've got your box and your asymptotes on there, you just want to draw a curve that starts at the points on the sides and curves up to the asymptote. So, oops, let's try that again. That's a little too straight. Yeah, it looks like that. Okay, and when you're done, hopefully you've used pencil, because our picture is going to look like a mess if we have all these dashed lines in here, so we're going to get rid of them. And hopefully I do not end up erasing the lines that we drew. Be extra careful. All right, success. Okay, so now let's go through and do the same thing with y. So we have y equals 0. If y equals 0, then we get x squared minus z squared over 9 equals 1. You just want to do the exact same thing, okay, except so there's another hyperbola. How do you tell if that's a hyperbola? Well, you have both the variables are squared, and one of them is positive and the other one is negative. Okay, and so the box in that case is we're still gonna have 3 and negative 3 for z, and then our other points are at x equals 1 and negative 1. And so our box is it's gonna look a little strange, but you're gonna go up here and then over. And you're going to go up here and then over. So it's the equivalent of what we just did, except with x. So the x-axis goes this way, so the top is going to align with the x-axis. And so that's our box. That's the equivalent. And then you want to draw an asymptote that goes through the corners of that. Okay. And so that's the equivalent of what we drew a moment ago, except with the xz plane. Again, the xz plane is probably the hardest to work with. And from there, you just want to start off at your point here and curve up to the asymptote, the dashed line, the angled dashed line that you drew. So let's see if we can do that. And the same thing downward and up and down. Okay, so I'm almost afraid to erase the dashed lines for fear of erasing those curves I just drew, because the curves are pretty good. All right, that's good enough. Close enough. Okay, so we end up getting these curves. Now, one little trick, so to what I just did, notice the top arrows roughly align with the top of the plane that this is graphed on, right? These curves on the sides were graphed on the YZ plane, and the YZ plane aligns with the Y axis. So the top corresponds to the y-axis. You could take a y-axis and set it on here. Maybe this one's a little bit low, but you could see it's roughly that's the case. And the same thing for the bottom. And now notice the corners here, they're on the XZ plane. The XZ plane aligns with the x-axis. If you took this line here and just set it on here, it would line up. So that'll give you the right kind of dimensionality to your picture if you go through and you do that. Okay, now we're pretty close here. The only thing that's really left is that this circle here doesn't really tell us what's going on up here at the top. And so what I'm going to do is I'm going to cheat. All right, so I'm going to say if I went through and went up to z equals 3 and were to plug this in, what would happen? All right, well, if I went in the if I went in the y direction, I would hit the curve right here. If I went in the negative y direction, I would hit the curve right here. If I went in the x direction, I would hit right here, negative x right here. And so I'm going to draw another circle like that. And then you could do the same thing down below here. And that is what a hyperboloid of one sheet looks like. It has hyperboloids for the edges, and it's all connected in one piece. All right, this one opens. See, the opening is about the z-axis. That is because the z has the negative. If the x had the negative, then the opening would be about the x-axis. If the y had the negative, then the opening would be about the y-axis. Okay, next. Let's say we have negative x squared minus y squared plus z squared over 4 equals 1. This is a hyperboloid of two sheets. The way that you can tell the difference, hyperboloids of two sheets have two negatives. Hyperboloids of one sheet have one. The general form for a hyperboloid of one sheet, at least the particular one that we're graphing, is the following. All right, let's draw ourselves a coordinate axis. Oops, wrong way. Okay. And then we can go through and generate our cross sections. So you could start off z equals 0. If z equals 0, then we get negative x squared minus y squared equals 1. Now there's no solution to that. That's not possible. So what does that tell us? At z equals 0, which corresponds to the xy plane, there's no part of the object there. We didn't get a cross section there. There's nothing at that level. If you want to think of the cross section like you're cutting through the object, you went to cut through and you hit empty air. All right, let's try x equals 0. If we do x equals 0, we get negative y squared plus z squared over 4 equals 1. All right, so this is, as we discussed, this is a hyperbola because we have squares for both, and one of them's negative and one's positive. So to go through and use the box method, what you do is you use the square root of the denominators, right? So we're going to have at plus or minus 2 for z, so 1, 2, 1, 2. We will have some points there. Maybe I did not explain this previously because the previous example we didn't have points. The one that's positive gets the points. The one that is negative, right? So take the square root of the denominator here, you get 1 and negative 1. That gets the kind of the long dashes that we're going to use to generate the box. Okay, so the positive one, points, the negative one, dashes, and then to draw the box, just extend upward from the dashes until you get to the point. Extend downward until you get to the point, and then draw the asymptotes that go through the corners. Okay, and then we're going to start here and we're going to curve over to the asymptote. the same thing down here. Okay, and then you can go ahead and erase some of your dashed lines. I don't want to get too close. I don't want to erase the line I just drew. That would be a shame. Okay, let's go through and do the same thing for y equals 0. So if y equals 0, we get negative x squared plus z squared over 4 equals 1. So that's going to be the same thing, except we're going to go, we'll have our dashes on the x-axis instead of on the y. So we'll go here, and there's 1 unit in the x. We'll say that's, well, maybe a little bit further than that for the negative x. So there we go. And then go up until you're across from the point at the top in the x direction, and then go over, and then down. Draw your asymptotes through the corners. Okay, and then from the point, you want to curve up to the asymptote. So we want to curve up like that, curve up like that, like that, and like that. And I'm not even going to bother to erase the dashed lines because it's too nerve-wracking. So the last thing that we need to do is kind of hard to tell based upon this, but right. So if we go up, this is up 1, up 2. If we go up maybe to a 3 or to 4, if we go up to 4, if we went in the y direction, we'd hit the curve here, negative y here. If we went in the x, we'd hit here, negative x here, and so you could go ahead and just draw a big circle up there. And then if we do the same thing down here, it looks like we'd hit here and here and here and here. And if you've done a good job, right, it should look like 2 bowls, right? So we've got a bowl up at the top and we've got a bowl at the bottom, a bowl facing upward and a bowl facing downward. Okay, so that's your picture for the hyperboloid of 2 sheets. And the way the facing or orientation of the hyperboloid is the term that's positive. It has is the axis around which it opens. So since z is positive here, that's why the bowl is opening around the z-axis. If x were positive, if we swapped these and x were positive and z were negative, then it would open around the x. You'd have bowls facing forward and back. And if we had the y be positive, we'd have bowls facing to the right and opening to the right and left. Okay, last one. Z squared equals 4x squared plus 4y squared. This is a cone. How can you recognize a cone? The format for a cone is z squared over c squared equals x squared over a squared plus y squared over b squared. Okay, so how do you recognize a cone, right? So all of the terms are squared. One of them is by itself, and the other 2 are on the opposite. So one's by itself, the other 2 on the opposite side, and that gives you the format for a cone. And they all have to be positive or negative. Let's see if we can sketch this. Okay, cross sections. So if you set z equal to 0, we end up getting 0 equals 4x squared plus 4y squared. The only solution to that is x equals y equals 0. If we set x equal to 0, we end up getting z squared equals 4y squared, which if you take the plus or minus root of both sides, you get z equals plus or minus 2y. Okay, and you could think of this as z equals plus or minus 2 over 1. Why? Now, why would I do that? It's because of the fact that the format for z equals plus or minus 2a, this is in the format of a line. All right, so what this is two lines. The cross sections are lines in this case. So to go through and draw the line, I've went through and I've put it into essentially like a slope intercept form. So the intercept is 0 and the slope is going to be 2 over 1. The way to handle the slope when you don't have x and y is that the z, the thing that's on the opposite side of the equal sign, corresponds to the numerator. The thing that's multiplied by this corresponds to the denominator. So this is saying that we're going to rise 2, we're going to go 2 in the z direction for every 1 in the y direction. So to go through and graph that, you could go up 1, up 2, over 1, and that would give you a point there. And then we could go through and draw a line that went through that point. And then the negative would be the same thing except for negative, right? We'd go down 1, down 2, over 1. And if you've done a good job, those should be symmetric. Okay. And then we could do y equals 0. If we do y equals 0, we get z squared equals 4x squared. Then z equals plus or minus 2x, or z equals plus or minus 2 over 1x. So this is the same thing. This is 2 more lines. This is saying go, for those lines, the slope is to go up 2 in the z direction, 1 in the x direction. So if we want to go through and say, all right, well, this is 1 unit in the x, then we would go up 2 and then over 1. So we'd end up maybe right about there. And you could go up 2 over 1, right about that. This point looks a little too far. Right, that 1 unit. It should be proportional. If that's 1 unit, 2 of those should be 2 units. It looks maybe be like more likely right about there, maybe. Anyway, and then we could go down 2 and then 1 in the x, down 2, 1 in the negative x. And then we could go through and draw yet another line. And then one more. Okay. And so those 4 lines are really not quite enough to tell what the object looks like. But what you can do is you can recall, hey, this at a height of 2, at z equals 2, I went 1 unit in the x, 1 unit in the negative x. So I've got points. And I went 1 in the y and 1 in the negative y. So I've got some points here. I could go through and just connect those points with a smooth curve. And you could do the same thing down here, down below. And you end up, well, that's not the greatest circle, but you get the idea. That gives us a picture that does look like a cone. And so that's our sketch for the cone. All right, so the last object that's actually in this section, I'm going to skip over because very, very difficult to graph. However, you may need to go through and do a little bit of research, and that is the hyperbolic paraboloid. So it looks like a saddle. Very, very, very difficult object to go through and graph. But it's one of those things that you might encounter if you're going through and working on problems that are related to quadric surfaces. So anyway, that's going to be it for this video. Thank you for watching. See you next time.